If you buy a $100,000 electric vehicle today, you are essentially buying a supercomputer on wheels. I mean, it packs enough raw, high voltage energy to power your entire house for, like, a week.
Right, yeah. It's an incredible amount of energy.
Exactly. And they're aerodynamically perfect. They've got these crazy silicon carbide inverters, super dense lithium-ion packs. But here's the ultimate irony, and honestly something that keeps automotive engineers awake at night. If a humble, old-school 12-volt battery just hiccups, that entire cutting-edge powerhouse comes to a violent, catastrophic halt.
It really is the single greatest paradox of modern EV architecture, because the high-voltage system, for all its massive power, is completely blind, deaf, and paralyzed without that low-voltage auxiliary grid. It's the ultimate Achilles heel.
And that is exactly our mission for this deep dive. We're looking straight into the electrical circuit and communication network layer of a battery management system, the BMS.
Right.
Specifically, we're unpacking two very specific diagnostic codes that mean this low voltage lifeline is failing. So we've got P0A8D, which flags that the 14-volt supply has dropped dangerously low, and then P0A8E, which means you've just been hit with a massive overvoltage surge.
And it's important to realize these aren't just minor nuisance codes like, oh, my radio stopped working. In the context of functional safety, these are the harbingers of a potential total system failure.
Wait, really? Like total failure?
Oh, absolutely. The 12-volt or 14-volt operating system, it provides the isolated operational baseline for the entire vehicle's brain. If that baseline collapses or surges, you can lose high-voltage isolation entirely.
Which sounds terrifying.
It is, because you risk the contactor relays losing their magnetic grip, and that can induce thousands of degrees of electrical arcsing right inside the main battery pack.
Okay, let's unpack this. Let's jump right into the physics of why that lifeline fails in the first place, starting with the low voltage drop, the P0A8D code. Because I think most people just assume a 12-volt battery just works until it's dead.
Right, like in a normal gas car.
Yeah, exactly. But in an EV, the dynamic load profile is just completely different than an old internal combustion engine car. We are dealing with massive instant loads from the electric power steering, electronic brake boosters, or like high-power thermal management fans.
Exactly. And the capability of the 12-volt battery to handle those transients, whether it's a traditional lead-acid AGM battery or even a newer 12-volt lithium-ion one, it degrades over time.
Sure.
With lead-acid chemistry especially, you're constantly fighting plate sulfation. As these lead sulfate crystals grow and, harden other plates, they reduce the active surface area. And simultaneously, you've got vibration and thermal cycling causing the physical shedding of that active material.
Right. And from a circuit analysis perspective, that physical degradation translates directly to a massive spike in internal electrical impedance.
Yes, exactly.
Because a healthy battery essentially acts as a giant decoupling capacitor for the entire low-voltage grid. I actually like to think of it like an acoustic dampener in a really complex hydraulic system.
Oh, that's a great analogy.
Yeah, like when that dampener is healthy, it absorbs the shock waves of all these valves opening and closing. But when the internal impedance spikes because of aging, it's like that dampener has just frozen solid.
Yeah.
Every sudden load demand sends a destructive pressure drop rippling across the entire network.
That hydraulic dampener analogy hits the nail on the head. When a transient load kicks in, say, the electric power steering motor suddenly demands 80 amps in a fraction of a second just to help you swerve. That sudden current spike against a high-impedance battery causes the bus voltage to sag severely. Yeah, and if the impedance is high enough, the voltage supplied to the BMS input pins can plummet from a healthy 13.5 volts straight down through the floor, dipping below 9 volts. And the moment the hardware detects that sub-9 volt threshold, boom, it trips the P0A8D fault.
Okay, so the brain of the car is essentially suffocating because the aging battery just can't push the current fast enough. That makes sense for the starvation aspect. But what about the other extreme, the P0A8E code? How does the 12-volt rail suddenly get hit with a high-voltage surge? I mean, an EV doesn't have an alternator.
Right, it doesn't.
So it's relying entirely on the high-voltage to low-voltage DC-DC converter, the accessory power module, to step the voltage down.
Correct. The DC-DC converter is constantly pulling from the 400-volt or 800-volt main pack and bucking it down to around 14 volts. And it operates using a highly complex closed-loop control circuit that rapidly switches power transistors. If that feedback loop deadlocks or, say, a low-side switching tube fails,
Mm.
you can certainly get an overvoltage condition. But the far more destructive phenomenon, the one that truly tests the hardware's armor, is the load dump.
Right, the load dump. And this is pure inductive physics at play, isn't it?
Oh, absolutely.
Because if the DC-DC is outputting maximum current, let's say 150 amps, to run the cabin heater fans, the seat heaters, the headlights, and to charge the 12-volt battery, and suddenly a main connection to the battery shakes loose from, like, a pothole, or a fuse abruptly blows, that massive electrical load just instantly vanishes.
And nature abhors a sudden change in current across an inductor. The magnetic field stored in the DC-DC converter's internal inductors and the vehicle's wiring harness itself suddenly have nowhere to go.
Yeah.
According to Faraday's law of induction, an instant drop in current multiplied by the inductance generates a massive flyback voltage.
So you're essentially creating a localized lightning strike inside the wiring harness. We aren't talking about a gentle, float up to 18 volts. We're talking about a transient spike of 100 volts or more happening in literal nanoseconds.
Exactly. A transient spike that aggressively seeks a pass to ground through the most delicate silicon on the board. This surge slams into the BMS circuitry, easily blowing right past the maximum voltage ratings of standard low dropout regulators and internal step-down chips.
So it just fries everything.
Pretty much. The voltage shoots well over 16 volts, immediately triggering the P0A8E fault, assuming the measurement circuitry itself hasn't been vaporized by the surge first.
Man, okay, so we have the battery aging out and causing severe voltage sag under transient load, and we have inductive load dumps causing triple-digit voltage spikes. But there's a third dimension to this root cause analysis that I find fascinating, mostly because it's just so deceptively simple.
You're talking about parasitic impedance.
Yes, parasitic impedance on the KL30 main power and KL31 ground lines, so a slightly loose bolt can actually shut down the car.
It is deceptively simple, but it is incredibly common. You have to remember, we are dealing with the physical realities of the automotive environment. The wiring harness, the connector crimps, the fuse box terminals, the chassis grounding points. They are subjected to brutal conditions.
Right, weather, salt, all of that.
Exactly. Moisture ingress leads to galvanic corrosion, and continuous vibration causes micro-shredding wear on the connector pins. It's constantly scraping microscopic layers of metal away until a hard, insulating oxide layer forms.
And this brings us back to dynamic voltage drop, but in a localized way. Because you could have a perfectly healthy 12-volt lithium battery putting out a rock-solid 13.8 volts, but if the primary KL31 grounding bolt that connects the BMS to the vehicle chassis has developed, say, a high-resistance layer of corrosion, you have a massive problem.
Yes, you do.
If the BMS suddenly needs to pull a high-current pulse, Ohm's law dictates that the current multiplied by that tiny bit of parasitic resistance will create a massive voltage drop directly across that single bolted connection.
Precisely. So the battery sends 13.8 volts. But 4 or 5 volts might be lost entirely as heat across that one corroded ground bolt.
Right.
By the time the power actually makes it to the processor pins, it's only seeing 8.5 volts.
Wow.
The system is starved, the P0A8D code triggers, and the vehicle shuts down. The most advanced silicon carbide inverter and lithium-ion pack on Earth can literally be brought to its knees by micro-fretting on a single, cheap steel bolt.
That is wild, which perfectly illustrates the stakes here. So if we know the environment is this hostile, that voltage is fluctuating wildly, dropping below the survival threshold of the silicon or surging to destructive levels, how does the BMS actually perceive these threats in real time? And more importantly, how does it defend the high voltage components from catastrophic damage?
Well, the defense has to begin with perception, which is why the BMS relies on an incredibly robust analog-to-digital converter, or ADC architecture. The physical voltage of the 12-volt lifeline is an analog continuous wave, right? But the microcontrollers operate in discrete digital logic.
Right, ones and zeros.
Exactly. The ADC bridges this by sampling the analog voltage thousands of times per second and quantizing it. But to do this accurately, the ADC must have an absolute unmoving baseline to compare against. This is called the reference voltage, or ref.
And this is where it gets incredibly tricky in a fluctuating power environment. If the 14-volt supply is sagging, the power feeding the chip that regulates the ref might also sag. I like to think of it like trying to measure the exact length of a piece of wood using a tape measure made out of elastic rubber.
That is a perfect analogy.
If your tape measure stretches, All of your measurements are inherently flawed, no matter how precisely you read the lines.
Exactly. And in the context of a high-voltage battery pack, a flawed measurement is exceptionally dangerous. If the ADC is reading cell voltages to determine the state of charge and its VREF is skewed, it might calculate that a lithium cell is at 3 volts when it's actually at 3.5 volt.
Oh, that's bad.
It's terrible. It could instruct the charger to keep pumping current into a fully charged cell, leading to thermal runaway and a catastrophic fire.
So how do you prevent the elastic tape measure scenario?
Through intense redundancy and aggressive self-diagnosis, which is mandated by ASIL-C safety standards. ASIL stands for Automotive Safety Integrity Level, and Level C implies a severe risk of injury if the function fails. So the BMS software architecture utilizes dual independent ADC channels to sample the lifeline voltage. Furthermore, the ASIL-C software module continuously runs self-diagnostic checks on the VREF itself.
I was actually reading through the tolerances on this, and the safety threshold is incredibly tight. If the power anomaly causes the VREF to drift by more than 50 millivolts, the system triggers a critical fault. 50 millivolts? I mean, that is a microscopic shift in a vehicle dealing with 800-volt drive system.
It sounds microscopic, yeah, but in a 12-bit or 16-bit ADC system, a 50 millivolt shift completely corrupts the quantization mapping. The moment the software detects this drift, it assumes its perception of reality is entirely compromised. It immediately halts all cell balancing, calculation, and thermal management tasks, and crucially, it actively commands the main relays to open, isolating the high-voltage battery. It chooses a known, safe shutdown over the unpredictable chaos of operating with a warped perception.
Okay, so the software acts as the first line of defense against corrupted data. But let's say the voltage drop isn't just a slight sag that warps the VREF. Let's say the KL30 line gets cleanly severed, or a transient load drags the voltage so low that the microchips physically cannot execute logic anymore. The software is just dead in the water. How do you prevent the physical, mechanical, high-voltage contactors from doing something disastrous?
This is where we cross from software into purely physical hardware-level protection. The undervoltage lockout, or UVLO circuit. To understand why UVLO is critical, you have to look at the mechanical reality of a high-voltage contactor.
Okay.
A contactor is essentially a massive electromechanical relay. You have these thick copper pads that must carry hundreds of amps of high-voltage direct current. To keep those pads pressed firmly together against the immense counterforce of heavy internal springs, you need a powerful electromagnet, a coil, which is driven by the 12-volt supply.
Right, and the force of that electromagnet is directly proportional to the current flowing through its coil, which is obviously dictated by the voltage of the 12-volt lifeline. If that voltage starts to drop, the magnetic pole holding those massive copper pads together starts to weaken, and the springs start winning the battle.
Exactly, and that transition phase is the most dangerous state in high-voltage engineering. Engineers call it the asymmetrical jitter arc zone.
That sounds ominous.
It is. If the voltage drops just enough that the magnetic grip is weak, but not enough to let the springs snap the contactor completely open, the vibration of the moving vehicle takes over. The copper contacts begin to bounce. They separate by a fraction of a millimeter, then smash back together at incredibly high frequency.
And when you separate two pieces of copper carrying 300 amps of 400-volt direct current by a fraction of a millimeter, the electricity does not just politely stop flowing. You ionize the tiny air gap between the pads. You create plasma.
You basically create a localized lightning storm inside the contactor housing. That electrical arc burns at thousands of degrees. In milliseconds, it will vaporize the surface of the copper contacts.
Oh, wow.
Yeah, it will melt them into a slag that welds the contactor permanently shut, which is a catastrophic failure because now the high-voltage pack can never be safely isolated. Furthermore, the vaporized copper coats the internal ceramic insulators, creating a conductive path that destroys the migum-isolation resistance of the entire vehicle.
So the UVLO circuit is essentially a hardware dead man's switch to prevent this plasma torch scenario.
Exactly. The UVLO is an analog hardware comparator circuit that monitors the coil drive voltage completely independently of the microcontroller. It has a hard-coded threshold, usually around 7.5 to 8 volts. The absolute millisecond the voltage drops to that threshold, the hardware comparator flips.
It doesn't wait for the MCU.
No, it forcefully and mechanically severs the drive signal to the contactor coil, utterly bypassing any software control.
It just violently pulls the plug on the electromagnet, allowing the heavy springs to snap the contactor completely and cleanly open before it can enter that jittering arc zone. It demands a binary state, right? like 100% tightly closed or 100% wide open, nothing in between.
Exactly. That immediate hardware override is crucial. But the BMS also has highly choreographed, state-dependent fail-safe responses if the microcontroller is still alive to manage the power drop.
Let's walk through those states, because how the car reacts when you push the start button versus when you are doing 75 miles an hour on the highway are very different scenarios. Let's say it's the wake-up stage. You get in the car, hit the brake, push the start button.
In the wake-up stage, the BMS initiates a pre-flight self-check. If it samples the KL30 line and sees the 12-volt auxiliary battery is at 9 volts or less, the software enacts a strict pre-charge lockout. It absolutely refuses to initiate the high-voltage relay sequence. The system main relay, the SMR, stays open. The dashboard might light up dimly, but the vehicle refuses to enter the ready state.
Which is annoying if you're trying to get to work, but it completely protects the high-voltage system from attempting to close contactors with inadequate holding force. But the more terrifying scenario is if you are already in the ready state. You are driving on the highway, a massive transient load hits, or a wire vibrates loose, and the voltage suddenly falls out from under you. Does the car just immediately snap the contactors open and kill the drive power?
It depends entirely on the duration of the drop, and this is where the engineering is truly brilliant. This is called the dynamic ride-through sequence. The BMS relies on massive internal capacitor banks.
Okay.
If the voltage drop is a transient sag, say lasting less than 50 milliseconds because an ABS pump briefly spiked the load, the local capacitors on the circuit board instantly discharge, acting as localized microsecond battery backups.
So they hold the voltage rails at a steady 3.3 volts and 5 volts for the microchips, totally decoupling the brain from the chaotic voltage drop happening out on the main 12-volt bus. The MCU doesn't skip a single clock cycle.
Right.
The software doesn't even realize the main power dipped. You, as the driver, feel absolutely nothing. The car just rides through the disturbance.
Exactly. But if that voltage drop persists beyond that 50 millisecond capacitive holdup window and the main 14-volt supply is still below the critical 7.5-volt threshold, the power management IC recognizes that a total blackout is imminent. The microcontroller is about to hard reset.
So how does it manage a safe shutdown when it knows it only has a few milliseconds of consciousness left?
It executes an emergency soft cutoff sequence. It's essentially a race against time. The BMS uses its last joules of capacitive energy to blast a high-priority CAN bus message to the Vehicle Control Unit, the VCU. It effectively shouts, "I am going dark. Derate the inverter torque to 0 immediately."
Oh, so it demands the motor stop pulling current before it dies?
Yes. The VCU instantly commands the silicon carbide inverters to stop switching, dropping the high-voltage current flowing through the main contactors from perhaps hundreds of amps down to under 5 amps. And only then, once the massive current load is removed, does the BMS release the contactor coils.
That is so smart. By shedding the current load first, it ensures that when those contactors do snap open, there is virtually no current left to create an arc. It's a meticulously choreographed safe landing sequence, executed in the split second before the brain completely shuts off, accompanied by a final dashboard warning telling the driver to pull over immediately.
It really is the difference between a safe highway shoulder deceleration and a catastrophic high-voltage hardware failure.
Knowing that a sudden drop to 7.5 volts forces this critical, desperate shutdown sequence, it makes you wonder how design engineers physically build a circuit board capable of surviving these chaotic environments and executing these lifelines flawlessly every single time. And I think that brings us to the design phase, the DFMEA.
Design failure mode and effects analysis. DFMEA is a highly structured, proactive methodology used to anticipate every conceivable failure mode of a component, calculate its severity, and design hardware countermeasures before a single prototype is ever manufactured.
And when we look at the DFMEA documentation for these 14-volt supply failures, the P0A8D and P0A8E scenarios, how severe is this considered by the engineering teams?
It carries a severity 8 rating.
Out of 10.
Yes. On a standard 1 to 10 scale, where a 10 is an uncontrollable vehicle fire or complete loss of steering without warning, an 8 is catastrophic. It represents a primary loss of vehicle propulsion and function. We are talking about continuous microcontroller resetting, total communication paralysis on the CAN bus, and the inability to monitor thermal limits in the pack. It is a critical functional safety hazard that mandates massive hardware over-engineering.
Let's talk about that over-engineering, starting with the power management IC, the PMIC, because this chip is basically the gatekeeper. It takes the wildly fluctuating 12 to 14-volt supply and regulates it down into the precise 5-volt, 3.3-volt, and 1.2-volt rails needed for the ADCs and the microprocessors. If the PMIC dies, everything dies.
Exactly, which is why the hardware requirements mandate that an automotive-grade PMIC must have an extraordinarily wide input voltage survival range. While its nominal operating target is 14 volts, it is designed to maintain perfectly stable output rails even if the input drops as low as 4.5 volts during a severe cold cranking transient. And it must survive continuous overvoltage conditions up to 28 volts and sometimes as high as 36 volts in heavy-duty applications.
But the PMIC can't handle a 100-volt load dump surge on its own. It needs bodyguards. And looking at the schematic of a BMS motherboard, you see a heavily fortified defensive gauntlet before the power traces even reach the PMIC. You've got anti-reverse P-channel MOSFETs designed to instantly block current if a technician hooks the 12-volt battery up backwards.
Yep. Very common mistake.
Right. And you've got massive ferrite chokes and front-end filter inductors to strip high-frequency electromagnetic interference off the line. But the ultimate shock absorber is the TVS array.
The transient voltage suppressor. These are the lightning rods of the entire electrical architecture.
I find the physics of TVS diodes fascinating because they operate on the principle of avalanche breakdown. Normally, they just sit there invisible to the circuit doing absolutely nothing. But when that 100-volt ISO 16750 dole load dump serve hits the board,
The TVS diode reacts in picoseconds. The moment the voltage crosses its specific breakdown threshold, say 24 volts, the internal PN junction of the diode transitions from an insulator to a highly conductive state.
it just opens the floodgates.
Exactly.
Yeah.
It essentially creates an intentional controlled short circuit to ground. It clamps the voltage, shunting the massive surge of current away from the delicate PMIC and dissipating the energy as heat within its own silicon structure.
It literally acts as a sacrificial energy sponge. It eats the 100-volt spike, clamping it down so the microchips downstream never see anything higher than their maximum survival rating. But absorbing a surge is only half the battle.
What about the other extreme? We discussed the 50-millisecond dynamic ride-through. How does the DFMEA process guarantee that the hardware can sustain the MCU when the power completely drops out?
This requires precise calculation of localized capacitance. Engineers physically integrate massive banks of low ESR decoupling capacitors directly onto the BMS circuit board. ESR stands for equivalent series resistance.
You need low ESR, because when the main power dies, a brownout event, these capacitors must discharge their stored energy instantly without internal resistance slowing the flow to act as that 50-millisecond lifeline.
I think of this like a localized, uninterruptible power supply, a UPS for the car's brain. If you're compiling code on your desktop computer and the neighborhood grid goes dark, your UPS gives you just enough time to save your work and safely shut down the machine before you lose your data. The BMS is doing the exact same thing.
Exactly. And the data it is saving is absolutely critical for the vehicle's survival upon the next reboot. During that 50-millisecond capacitive lifeline, the microcontroller rapidly writes the historical state of charge, the exact measurement of how much energy remains in the high-voltage pack, along with any active diagnostic trouble codes, directly to non-volatile EEPROM or flash memory.
Because if the MCU loses power mid-calculation before that memory block is successfully written, the data is just scrambled. When the driver eventually replaces the 12-volt battery in the BMS reboots, it reads that corrupted memory block. It generates a fatal checksum error. It looks at the corrupted state of charge data, realizes it has absolutely no idea how much energy is in the high-voltage pack, and actively refuses to close the SMR contactors because it can't guarantee it won't overcharge or over-discharge the cells. The car is effectively bricked because of a corrupted save file.
And that is precisely why the DFMEA process mandates those low ESR capacitors.
Yeah.
They mathematically guarantee the MCU has the clock cycles required to securely close the file system before the voltage rail collapses completely.
Man. So, on a computer screen, in an ideal CAD environment, the board is invincible. It has TVS lightning rods and massive capacitor lifelines. But translating that perfect digital design into millions of physical units on an assembly line is a completely different war. How do factories guarantee that this heavily armored hardware doesn't fail due to a manufacturing defect?
This is the domain of PFMEA, Process Failure Mode and Effects Analysis. The singular goal of PFMEA is variance control. They use a highly structured framework called 5M1E, which analyzes every potential variable across 6 categories: man, machine, material, method, measurement, and environment. If you can control the variance in those 6 areas, you can guarantee a perfect product.
Let's apply 5M1E to the exact components we just discussed. Those massive TVS diodes and low ESR capacitors are physically large. They contain a lot of copper and ceramic. So from a thermodynamic perspective, they have a massive thermal mass compared to, say, a microscopic 0402 surface mount resistor sitting right next to them.
And that thermal mass disparity is an absolute nightmare for printed circuit board assembly, or PCBA. During the reflow soldering process, the entire circuit board travels through a massive multi-zone convection oven designed to melt the solder paste and fuse the components to the pads. Because the TVS diodes and large capacitors act as heat sinks, they absorb thermal energy much slower than the tiny components.
Which means if the reflow oven isn't perfectly tuned, the solder paste under a tiny resistor might completely liquefy, while the paste hidden underneath the massive capacitor barely even reaches melting point.
Leaving you with a cold solder joint. A cold joint is brittle, lacks proper intermetallic bonding, and possesses inherently higher electrical resistance. To combat this, the PFMEA defines the reflow soldering temperature curve, the TCT profile, as a key control characteristic. The specific ramp-up, soak, reflow, and cooling times are aggressively monitored and dynamically adjusted based on the thermal mass density of the specific board design.
But they don't just trust the oven. I mean, the inspection protocols are staggering. Every single board coming out of that oven passes through 100% 3D solder paste inspection, or SPI, and 3D automated optical inspection.
AOI, yes.
Right. We are talking about laser profilometry and high-resolution cameras building topographical maps of every single solder joint, looking for microscopic cold joints, insufficient wetting, or hairline fractures.
Because a microscopic crack that passes basic electrical testing in the factory will eventually propagate due to coefficient of thermal expansion mismatches and, highway vibration. 6 months down the line, that crack opens completely, severing the connection to the TVS diode or the lifeline capacitor. The armor falls off, and the next load dump destroys the board.
So the soldering is mathematically perfect, but what about the environment? The BMS is sealed inside a metal battery enclosure, bolted to the underside of the car. It's subjected to extreme temperature swings. If you park outside on a freezing night and then start driving, the high-voltage cells and the bus bars rapidly heat up inside that icy metal box.
You are creating the perfect conditions for internal condensation, dew, and frost to form directly on the BMS circuit board. And water, particularly water carrying dissolved contaminants from the manufacturing environment, is highly conductive.
And here's where we tie it back to the very beginning. Remember those high-frequency ADC sampling pins, the ones programmed to trigger a total high-voltage shutdown if the ref shifts by a mere 50 millivolts?
Exactly. If a microscopic drop of morning dew bridges the gap between those tightly packed ADC pins, it creates what engineers call parallel leakage. It's a tiny high-resistance electrical short circuit. That parallel leakage pulls the reference voltage down. The software detects the ref shift, assumes the hardware is failing, and violently commands the contactors to open. The car literally shuts down on the highway because of a drop of condensation.
That's nuts. To prevent this, the PFMEA process demands conformal coating. But this isn't just like spraying a layer of clear coat from an aerosol can.
Far from it. They utilize 100% automated high-precision vacuum dispensing systems. The BMS board is placed in a vacuum chamber, and a specialized high-density dielectric resin is applied. The vacuum environment is critical because it draws out any microscopic air bubbles trapped under the components.
Oh, because if an air bubble remains, it acts as a tiny moisture trap, eventually leading to corrosion. And they verify this using UV tracers mixed into the resin, right? The 3D optical inspection cameras hit the board with blacklight to ensure that every single high current pin, and specifically the high impedance ADC sampling pins, have a perfectly uniform millimeter of dielectric armor. It entirely seals the silicon away from the physical environment, completely eliminating that parallel leakage failure mode.
It isolates the board from the environment, yes. But eventually that perfect board must be bolted into a vehicle assembled by human beings. And humans introduce the highest degree of variance in the 5M1E model. Earlier, we discussed the devastating effects of parasitic impedance on the KL31 ground line, how a slightly loose bolt or a bit of paint can cause dynamic voltage drop and starve the PMIC.
Right. How do you guarantee that a line worker at an automotive plant perfectly torques thousands of grounding bolts a day into perfectly clean metal?
You don't rely on the human. You employ poka-yoke, a philosophy of mistake-proofing the process so the error is physically impossible to make. First, you remove the human from the surface preparation entirely. Before the KL31 terminal is attached, a robotic end effector physically grinds the vehicle's painted body panel down to bare, highly conductive metal at the exact grounding point.
Zero paint, zero resistance.
Then, for the fastening itself, the worker uses a highly advanced torque angle, smart servo tightening system. Traditional torque wrenches are flawed because they only measure the friction of the bolt turning. If the threads are dirty or cross-threaded, a standard wrench will click and say it's tight, even though the terminal is still totally loose.
But a torque angle system measures the rotational force and the exact degrees of rotation. It actually drives the bolt into the plastic deformation yield zone of the metal.
Yes. The specification is merciless. Exactly 9.0 plus or minus 0.5 newton meters of force, achieved within a strict 30-degree to 45-degree rotation window. If the rotation angle is too small, it means the bolt is cross-threaded. If the angle is too large, it means the bolt is stripping the threads.
And here's the ultimate poka-yoke implementation. That specific smart servo gun is continuously transmitting its telemetry via Wi-Fi to the factory's manufacturing execution system, the MES. If that specific worker on that specific chassis pulls the trigger and the gun registers 9 newton meters but only 20 degrees of rotation, the MES instantly flags a critical assembly failure. It stops the conveyor belt.
Yep.
It literally forbids that chassis from moving to the next station until the grounding bolt is removed, the threads are retapped, and the perfect torque angle curve is achieved and logged into the vehicle's permanent birth record.
It mathematically guarantees that parasitic contact impedance is eliminated right at the point of origin.
It is an obsessive level of manufacturing control, but they still don't trust it. Because before that perfectly bolted, perfectly coated board is allowed to leave the module assembly line, it has to survive one final hurdle: the end-of-line, or EOL, power dip screening.
They want to catch any infinitesimal defect in the PMIC or the capacitor banks before it ships. So every single unit is plugged into an automated test fixture that subjects it to an ISO 16715-2 power dip test. The fixture violently drops the 14-volt input supply down to 4.5 volts for highly specific durations, 15 milliseconds, 30 milliseconds, 50 milliseconds.
They are actively trying to trigger the ref fault and the P0A8D code.
They are forcing the board to rely on its localized capacitive lifelines. During these artificial brownouts, high-speed CAN bus analyzers monitor the board's communication. They ensure that not a single frame of data is dropped, no unexpected micro-resets occur, and the ADC reference voltages remain rock solid. Only boards that demonstrate absolute flawless survival under these induced power dips are cleared for integration into a battery pack.
Which brings us to the final and, I think, most brutal phase of engineering. The DFMEA designed the armor. The PFMEA guaranteed the armor was built flawlessly. But before an automaker will sign off on a new platform and legally sell it to the public, the engineers must definitively prove that the design will survive the absolute worst-case real-world scenarios over a grueling 15-year life cycle. This is the design verification plan and report the DVP&R mass production validation.
In the DVP&R phase, the goal completely shifts from building to destroying. Engineers subject the mass-produced hardware to extreme edge cases to validate that the theoretical safety margins actually hold up in physical reality. Let's start with validating the software's dynamic ride-through using HIL, or hardware-in-the-loop, testing.
HIL testing is fascinating. You take the actual physical BMS circuit board, but instead of putting it in a car, you plug its wiring harness directly into a massive multi-rack supercomputer. The supercomputer runs a high-fidelity physics model of the entire vehicle. It feeds the BMS fake high-voltage cell telemetry, fake motor inverter noise, fake temperature data. The BMS completely believes it is driving down a highway.
And while the BMS is happily managing this simulated drive, the engineers use programmable high slew rate power supplies to violently attack the physical 12-volt feed powering the board. They simulate the exact dynamic voltage drops caused by a failing auxiliary battery and heavy transient loads. They plunge the input voltage from 14 volts down to the 4.5 to 7.5 volt danger zone in a single millisecond.
And what defines a pass or fail during the simulated attack?
They hold the drop for specific intervals. For drops of 50 milliseconds or less, the validation standard demands a zero reset condition. The internal 3.3 volt and 5 volt rails must remain unperturbed. High-speed oscilloscopes monitor the silicon logic pins, and CAN network loggers verify that communication remains continuous. The board literally cannot flinch.
But what if they simulate a total failure? Like, they hold the voltage below 9 volts for longer than 100 milliseconds?
Then the criteria flips entirely. The system is now required to fail, but it must fail with absolute precision. The standard dictates that within exactly 1.0 seconds of the voltage crossing the threshold, the BMS must detect the fault, log the P0A8D trouble code, broadcast the emergency torque derate command to the simulated VCU, and completely lock out the high-voltage SMR precharge sequence. Wow. If the software takes 1.1 seconds to execute the lockout, the test fails, and the entire software architecture must be redesigned.
So they demand perfect resilience for short drops and perfectly choreographed suicide for long drops. But HL testing is mostly evaluating the software and the capacitive lifelines. How do they validate the hardware armor? How do they prove the TVS diode can actually survive a load dump without turning into a puff of smoke?
They utilize specialized electromagnetic immunity surge generators to perform the physical load dump validation. They inject the infamous ISO 1677 Fulvine 2 Test A and Test B pulses directly into the 14-volt pins of the BMS connector.
Yeah.
We're talking about physically shooting 100 volts with massive current backing it into the board for a sustained 400 milliseconds.
It's an intentional lightning strike, and the standard here is that the TVS array must undergo avalanche breakdown in nanoseconds, clamping the 100-volt surge down to a safe 28 or 36 volts, shunting the heat to the PCB ground plane.
And crucially, the TVS diode itself must not sustain permanent physical damage. It must survive repeated strikes. Furthermore, the voltage monitoring circuit must recognize the clamp surge, immediately trip the P0A8E high-voltage fault code, and lock out the ready state, again within that strict 1.0-second safety window.
Okay, so the logic board can survive spikes and dips, but the logic board is just the brain. The true danger, as we established early on, is the physical contactor relays entering that asymmetrical jitter arc zone. How on earth do you test that the hardware UVLO circuit actually prevents thousands of degrees of plasma from forming inside the battery pack?
You run the 100-amp arc prevention test. This is where DVP&R gets visceral and highly dangerous. Engineers place the BMS and the actual high-voltage contactors inside a blast-proof test cell. They close the contactors and push 100 amps of raw 400-volt direct current directly through the physical copper relay pads.
So you have a massive amount of lethal energy flowing through the system.
Exactly. And while that 100-amp DC load is flowing, they intentionally choke out the 12-volt coil supply. They ramp the voltage down slowly, pulling it down at a rate of 1 volt per millisecond, intentionally trying to force the electromagnet to weaken and allow the spring to bounce the contacts.
They're aggressively trying to induce the jitter arc zone while under heavy load.
Yes. They're testing the exact millisecond the hardware comparator trips. The instant the supply crosses the critical 7.5-volt UVLO threshold, the analog hardware must forcibly sever the coil drive current, ignoring any input from the microcontroller. High-speed, high-voltage oscilloscopes are wired directly across the contactor terminals.
What are they looking for on the oscilloscope trace?
They're looking for a completely clean voltage step. To pass validation, there must be absolutely zero chattering and zero duration of plasma arcing under that 100-amp load. The physical separation of the copper pads driven by the internal springs must be instantaneous and absolute, cleanly breaking the high-voltage circuit, even as the low-voltage supply driving it collapses.
It is the ultimate proof of the hardware dead man switch. But even if the circuitry is perfectly designed to handle electrical stress, it has to survive physical and environmental torture. That leads us to the final hurdle, the thermal shock and 500-hour freeze roast.
This test targets the fundamental metallurgy of the manufacturing process. The fully assembled, conformal-coated BMS boards are placed into multi-chamber environmental shock units. The board is soaked at negative 40 degrees Celsius until the core of the PCB is frozen solid. Then, a mechanical elevator violently transfers the board into a roasting chamber at 85 degrees Celsius. That's 185 degrees Fahrenheit.
And the transition is brutal. The specification demands a temperature rate of change of greater than 10 degrees Celsius per minute. You are subjecting the materials to massive, rapid thermal expansion and contraction.
They run this continuous freeze-thaw cycle unceasingly for 500 hours. Often stacked simultaneously with multi-axis electrodynamic shaker tables, introducing random high-G highway vibrations.
And they are specifically attacking the thermal mass disparity we talked about during the PFMEA soldering process. The massive copper pads of the TVS diodes expand at a completely different rate than the fiberglass FR4 circuit board, which expands at a different rate than the ceramic low ESR capacitors.
That coefficient of thermal expansion mismatch creates immense shear stress directly on the tiny droplets of tin silver copper solder holding the components to the board. They're trying to literally tear the solder joints apart through sheer thermomechanical fatigue.
And after 500 hours of this torture, it's not enough that the board simply powers on. The validation criteria goes down to the microscopic level with a metallurgical autopsy.
That's right. They take the surviving boards, embed them entirely in blocks of clear epoxy resin, and use diamond saws to physically slice the PCB and the solder joints perfectly in half. They polish the cross-sections and place them under high-powered scanning electron microscopes.
They're looking at the grain structure of the metal itself.
They're measuring the propagation of fatigue cracks along the intermetallic compound layers. In a severe thermal shock test, microscopic stress cracks will inevitably form. But the validation standard dictates that the cumulative length of those cracks must account for less than 10% of the joint's total cross-sectional area.
So if a crack has propagated through 11% of the joint, the engineering team has failed. They have to go back, change the reflow oven temperature profile, perhaps change the geometry of the copper pad on the PCB, and run the 500-hour test all over again.
They demand a process that is mathematically incapable of failing in the field. This statistical rigor applies all the way down to the poka-yoke grounding bolt. During validation, they analyze the torque angle data from thousands of fastening cycles to calculate the Statistical Process Capability Index, or CPK. The standard requires a CPK of greater than or equal to 1.67.
For those who don't dream in statistics, a CPK of 1.33 means your manufacturing process is highly capable, sitting comfortably within a 4 sigma spread, producing almost zero defects. A CPK of 1.67 pushes that into the realm of a 5 to 6 sigma spread. It mathematically proves that the natural variation of your robotic torque gun and your threaded holes is so infinitesimally small that the probability of producing a loose ground bolt one that could cause the P0A8D voltage drop is practically zero.
It's the culmination of everything we've discussed. The design, the software, the manufacturing, and the validation all interlocking to create an impenetrable fortress around a single, highly vulnerable point of failure.
And when you step back and look at the entirety of what we've covered, the sheer density of the engineering is staggering. We started by looking at two simple diagnostic codes, P0A8D and P0A8E, triggered by a failing 12-volt battery. But behind those codes lies a hidden war zone. We are talking about the chemical kinetics of sulfating lead-acid plates, the inductive physics of a 100-volt load dump, the nanosecond quantization of dual ADCs, the metallurgical realities of cold soldered joints, the plasma physics of a jittering high-voltage contactor, and the 500-hour thermomechanical torture chambers. All of this effort, millions of dollars in R&D and manufacturing oversight, is deployed just to ensure that a cutting-edge electric vehicle can safely stay powered on when you turn the steering wheel or hit a pothole.
It perfectly illustrates the reality of functional safety in modern automotive engineering. Every millimeter of copper trace, every single line of ASIL-C code, and every microscopic intermetallic bond in a drop of solder carries the immense weight of the vehicle's survival. There's simply no such thing as a simple low-voltage system anymore.
Which leaves me with a lingering philosophical engineering question to mull over. If you're listening right now, think about this. If our cutting-edge 800-volt electric vehicles, these marvels of silicon carbide and lithium-ion density, are fundamentally inextricably tethered to the vulnerabilities of a legacy 12-volt auxiliary system, will future engineering paradigms ever break this dependency? Will we eventually develop the semiconductor technology to safely allow the high-voltage pack to step down and run its own brain directly, completely eliminating the 14-volt lifeline? Or are we destined to forever build increasingly complex, mathematically flawless hardware fortresses just to protect our supercomputers from the humble, aging 12-volt battery?